Hello. In this video, I'd like to show you how to graph this, which is a circle of empty space outlined by a bunch of tangent lines. So let's get started. First, let's review how to graph a normal circle. That's x squared plus y squared is equal to 1. The reasoning behind this is the x makes one leg of a right triangle, the y component makes another leg of the right triangle, and then 1, or your radius, is the hypotenuse, right? So x squared plus y squared is equal to 1 by the Pythagorean theorem. There's actually another way to graph a circle, though. Basically, you say that the x component is equal to cosine of t, and the y component is equal to sine of t, and let's actually add a slider for t. And basically, as you change t, this point goes around the circle. So for all values of t, this graphs the circle. So what's going on here is t is actually the angle, right? So in this case, it's in radians. So let's go to like pi radians, right? In which case, we'd be exactly halfway around the circle. And in this case, so cosine of pi is -1, sine of pi is 0, so then the point goes to -1, 0, right? But let's keep t moving around. And what's useful about this form of a circle is now we can take a point that's on the circle, cosine of t, sine of t, and we can plug that in to the point slope version of a line. What's point slope? It tells us that if we have y minus some value b is equal to m times x minus some value a, and basically what this does, let's plot the point AB, is it gives us a line of slope m that goes through the point AB. So we can change the slope, change the coordinates, and we get a line. So what we're going to try and do is make point slope form for the tangent line to a circle, which means that it's going to sit on the circle at that point, cosine of t, sine of t, and only hit it at one point. So it's going to kind of be like that. The trick is doing this so it works for every single value. So we can start by saying if y minus b is equal to m times x minus a, if that goes through the point AB, that means we want to swap a out with cosine of t, and we want to swap b out with sine of t. And see, now this goes through the point on our circle. We can change that point. The line goes through that point now. But as you can see, the slope doesn't change along with it. We want this line to rotate around the circle as we change the point. So unfortunately, in order to get the slope of the circle, you need to use calculus, which is a little beyond the scope of this video. If you're curious, just look up something called implicit differentiation. But I'm going to make an argument, an intuitive argument, for what the slope of a circle is. So notice that whenever y equals 0, which is over here and over here, right, on the two extreme points of the circle, whenever y equals 0, the circle is pretty much going up and down, right? That's a slope of like infinity pretty much, or it's a slope that you get from dividing by 0, right? Your circle's just blowing up to infinity in slope. And notice that whenever x equals 0, which is up at the very top of the circle and at the very bottom, the circle's pretty much flat. It has a slope of 0, right? So that means that whenever x is 0, the graph is 0, which means maybe that the slope is going to have something involving, hang on, my picture is getting in the way there. That means that x will be on the numerator and y will be on the denominator. Why? Because that way, whenever y is 0, it blows up to infinity. Whenever x is 0, it stays at 0, right? So perhaps that is the equation, the formula for the slope of our circle. However, let's look at a point that disproves this, because this is along the right lines, but not quite right. Let's go to about right here. This is the square root of 2 over 2 in both the x and y direction. This is where the x component and the y component are equal. So if x is equal to y and the slope is x over y, that means the slope right here should be 1. So let's move the slope to 1, and you'll find that that doesn't work at all, right? That is not tangent, and that's not the slope we want. However, let's try -1, and you'll see that that looks like a very good match, right? And also, t equals 0.8, that's an approximation. Square root of 2 over 2 is obviously irrational, but for our purposes, this is good enough. But as you can see, where our x over y estimate is off by a negative sign. So we're just going to add a negative up here to our slope, negative x over y, right? And let's test that this works. So we're going to go over to here. This is when x is going to be equal to negative square root 2 over 2, y is going to be equal to positive. So when you divide that and then multiply by a negative, you're just going to end up with a slope of 1. And slope of 1 looks pretty correct. You can try this out with a bunch of other points. You'll find that negative x over y will give you the slope for any point on the circle. However, if we just plug negative x over y in right here, that doesn't give us a tangent line, right? Because we want the slope for any given point. And the trick is to convert negative x over y into trigonometry, just like how we converted x squared plus y squared equals 1 into cosine of t, sine of t. So we're going to say m is equal to negative x over y down here. But keep in mind that x, we said, was equal to cosine of t. And let's ignore what the graph's doing over there for a second. Y was equal to sine of t, right? So let's just plug in cosine of t and sine of t into this formula for the slope and see what comes out. So we get that the slope m is equal to negative cosine of t, we're replacing that for x, and sine of t, right? Tangent is sine over cosine, so cosine over sine is 1 over tangent. So we get that the slope is -1 over tangent of x, tangent of t, right? So if we plug -1 over tangent of t into our point slope formula and delete these graphs which are messing everything up, and then adjust t, we'll see that we now have a line that rolls around the circle. That's pretty cool. And one minor side note I want to point out is when slopes are perpendicular to each other, when two lines are perpendicular to each other, their slopes are negative reciprocal. So apparently, a tangent line gives us -1 over tangent of t, right? That's our slope. So that means this should be perpendicular to just a line with a slope of tangent of t. And, hang on. Oh yeah, we need parentheses around tangent. And look, now we have a circle that is always perpendicular. Or now we have a line that's always perpendicular to the outside of the circle. So I thought that was a cool little side note. Converting this back to our original, we now have our line that spins around the circle. So we're actually almost there to what we graphed originally, although it might not look like it. Let's move our equation all the way up to the top. Change the color to like blue. And then, oh, why did this disappear? Oh, t is equal to 0. There we go. See, when t is equal to 0, the slope will go up to infinity because you're dividing by 0, and the calculator doesn't like that. Anyway, so now the trick to graphing the disappearing circle is just to make it so t takes on a whole range of values. In Desmos, what you do is you say t is equal to every single number from 1, comma, dot, 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 up to, say, I don't know, 10 for starters. Ta-da! And we're going to get rid of these points because they mess it all up. That doesn't look like a circle, right? It's just because we don't have enough sample points, right? So let's instead take this up to 100. Whoa, that looked a lot like what we originally had. Let's take it up one more time up to 200, and now we have this really, really cool looking graph. You zoom out, you actually get all these cool little sunshine patterns. Then you go in, and you can see that circle is just cut out. So we can actually make some modifications to this. Let's add something to t. Let's say b. b is going to be on a slider. What this does is it rotates our entire graph. The computer gets a little laggy when you're doing this up at 200, but if you do it up at, like, say, 10 like before, you can easily see it rotating. Maybe let's move it up to like 50. That looks very cool. And you can also adjust the radius of the circle, right? What you would want to do is make it so that you put R here, and you would blow up the radius. Ta-da! So let's pause it, move this back up to 200, and there you go. You can just copy this formula, or better yet, try and recreate it using all the intuition you gained over the course of this video. And now you can graph a circle by graphing all the lines tangent to it. Thanks for watching, and please check out some of my other videos. Bye!